Hello students, welcome to the physics classes by CVR YouTube channel. In last lecture, we have discussed about different types of stress and strain and the calculation of stress and strain and different problems related to the calculations of stress and strain. So now in this lecture, we are going to discuss Hooke's law and stress strain curve. So first of all, according to Hooke's law, if the deformation is small, then stress is directly proportional to strain. So we can say stress is directly proportional to strain if the deformation is small, or else you can also write it like within the elastic limit stress is directly proportional to strain. Within the elastic limit, as stress is directly proportional to strain, we can say stress by strain is constant. Here the proportionality constant is known as coefficient of elasticity or it is also known as modulus of elasticity. So from this statement what we can understand is Hooke's law is an empirical law. It is not universal law and it is not applicable in all the situations. It is applicable only when the deformation is very small, within the elastic limit only, right? So that is why we can say it is empirical relation or empirical law. So here we have studied three different types in stress as well as strain depending on how the force is being acted, correct? So in the same way we have three different types of moduli of elasticity. So the discussion of different types of modulus of elasticity will be in the next lecture. So now we are going to focus mainly on stress strain curve. Stress strain curve. See students, here we are going to understand how stress and strain are related graphically. For that purpose, we will be taking a simple situation. The situation is like a wire is connected to the ceiling. Now, the free end of the wire is connected to a load. So here what we have to do is, first we have to note down the actual length of the wire. Now, once the load is attached to the free end of the wire, so you have to note the elongation in the wire. So with the help of radius of the wire, see here radius of this wire can be calculated with the help of screw gauge, and as we know about the load, you can calculate the stress, and as you can measure the change in length, so you can also calculate strain. note down the stress corresponding strain. Right? Now, increase the load, say from W1 to W2. You are adding weight or load to the wire. Now what we can notice here is increase in the length of the wire again. So for the corresponding increase in stress, we notice increase in strain. So if you perform this experiment and if you note down the data and then if you draw graph between corresponding values of stress and strain, that is as follows. Say here, stress is taken along y-axis, strain is taken along x-axis. Right, students? Now, in the beginning we notice straight line graph up to some extent. So up to this point it obeys Hooke's law. We can say between O to A, the wire obeys Hooke's law. Right? So then body is said to be elastic body between O to A, or you can say it shows elastic behavior. Between O to A, stress is directly proportional to strain and it obeys Hooke's law. At any point between O and A, if you remove the load attached here, the wire regains its original shape and size. So that is why we can say the region, or you can say the point A as proportionality limit. Point A is known as proportional limit. Right, students? Point A is known as proportional limit because between O to A, stress is directly proportional to strain. Now, when you add further load, like if you increase the stress further, we notice this kind of graph. So, up to point B, what we can say is between A to B, stress is not directly proportional to strain, but what we can expect here is when you remove the load between A to B, what we can say, body regains its original shape and size. So we can say point B as yield strength. Yield strength. Right? Or you can also say it as elastic limit. A limit to the elastic behavior of the material body. Now, with the further increase in load, so we can say up to point D. See, between B to D, between the points B to D, the region is known as plastic region. D or up to the next region, next point E also, that is fracture point. So we'll discuss about that later in this lecture itself. So now here between B to D, wherever you remove the load, Wherever you remove the load, the wire do not come back to the original state. You can say it do not come back to the original shape or size. So at any point here, if you remove the load, so stress is 0. Even though the stress is 0, strain is not 0. So it will set permanently at one particular point. Say it will be settling here. So this is said to be permanent set. This is said to be permanent set. It will set permanently. It won't regain to its original shape and size. Right, students? So at this particular region between B and D, when the stress is removed, body will not regain its original shape or size. Now beyond point D, even then there is no stress, there is a strain. So at one particular point called E, fracture takes place. The wire will break, or you can say that is a fracture point. So point E is known as fracture point. So D is ultimate tensile strength. That is like a breaking stress. The corresponding point D is stress corresponding to point D is ultimate tensile strength or breaking stress. The stress corresponding to point B is known as the yield strength. Yield strength. Right, students? Now, so here point D is known as, or the stress corresponding to D is known as ultimate tensile strength. So here we discuss in detail, furthermore points in detail about this particular graph. So here after point D, the wire will flow like a liquid, right, beyond this particular point. So here itself we will study few conclusions, such as if, or you can say region beyond B is known as plastic region. So if plastic region is less, then it is said to be brittle. The material is said to be brittle if the plastic region is less. If plastic region is more, then the material is said to be ductile. Then the material is said to be ductile. If the plastic region is small, that is said to be a brittle material. If the plastic region is more, the material is said to be ductile. See, in few situations, such as rubber, even though there is more elastic region, for most of the region, Hooke's law does not obey. Such materials are known as elastomers. Elastomers are nothing but, even though the elastic region is more, most of the region does not obey Hooke's law. Example, tissue of aorta and rubber. Corresponding stress strain graph of this situation is like this approximately. So there is no appreciable plastic region in this case. There is no appreciable plastic region in this case. Right, students? And here itself we talk about two more terms such as elastic after effect. Elastic after effect is nothing but the average delay in regaining original shape and size of a material body is known as elastic after effect. For example, for a perfectly elastic body, elastic after effect is elastic after effect is 0 because there is no delay in regaining the original shape and size for the perfectly elastic body. For perfectly plastic body, elastic after effect is infinity. Right, students? And one more term you have to understand is elastic fatigue. Elastic fatigue is nothing but, say for example, a material is undergoing stress repeatedly. Say we are using rubber repeatedly, when you are stretching the rubber repeatedly, so many times. When that is undergoing stress in a repeated manner, it loses its elastic nature. So that particular phenomenon is known as elastic fatigue. Right, students? And one more simple application. So here, steel is used to make springs. The reason is steel is more elastic than rubber, and for a given or applied stress, the deformation or strain in the steel is less. Right? So these are different points in the stress strain curve, and one example we can discuss. Say if they are giving two graphs. Say we have stress strain curve of two different materials. This is material B. This is material A. So they may ask questions such as, which is more brittle, which is more ductile, which is more strong. So first of all, to decide which is brittle, which is more brittle, which is more ductile, say for example, first to decide which is more brittle. So to say any material as a brittle, what is the condition? It should have less plastic region. So out of the materials A and B, which is having less plastic region? B. So you can say B is more brittle because of less plastic region. Next, plastic region is more in ductile. So we can say A is more ductile. And to decide which is stronger, we can understand with the help of stress. The material which can withstand more stress is more strong. Here, which material can withstand more stress? Material A. So that is why you can say A is stronger than B. Material A is stronger than B because of the reason that the strength can be determined by stress. What maximum stress, or the material which bears more stress is more stronger. Right, students? So this is all about stress strain curve. So few more points we will be discussing in the upcoming lectures. We'll cover few more points. So this is end of the lecture. Take care. Bye bye. We'll meet in the next lecture.